Okay, this week in our parent course, we're going to be covering something called the chain rule. The chain rule has to do with taking derivatives of composite functions. So in our support course this week, we're going to be talking about composite functions and working with those. So what is a composite function? Well, a composite function is a function that's formed using something called function composition, which is where we take two functions, f and g in this case, and we make one function the input of the other one. So we oftentimes will write it this way, f of g of x. Not so much in this course, but in other courses you might also see it written this way with this little circle between the two. We will be sticking pretty much to this notation though. The way we read this is f of g of x. And basically what function composition does is it forms a new function out of these two, where if you plug an x into it, that x first gets passed into this g of x function. G of x will do whatever it does to that input and it will produce an output. But the output of g of x will be used as the input for f of x. So it's a couple of steps there to get to a final output. So here's an example. F of x equals the square root of x, and g of x is equal to x squared minus 2x plus 5, and we want to evaluate the following. So here, we want to find f of g of 1. Because g is on the inside of those parentheses, we evaluate that first. I'm plugging a 1 in for g of x. That's 1 squared minus 2 times 1 plus 5. Okay, notice I just plugged the 1 directly into g, and I'm going to work that out. That's f of, let's see, 1 squared is 1 minus 2, that'd be negative 1, plus 5, that's 4. So even though I plugged in a 1 for g, it produced a 4, and now that 4 will be used as an input for this f here. What is f? It's the square root function, square root of 4, which is 2. So you see that we have two steps there. We first work with g, get an output, use that output as an input for f. Let's do the same thing, but the other way around. Let's do g of f of 1. So g of f of 1, f of 1 is the square root of 1. That's what f does to its inputs. It takes their square roots. So that's what that's equal to. Square root of 1, of course, is just 1. So we have g of 1 now. What is g of 1? Well, we already found g of 1 right here. Remember, g of 1 was actually something we started with in this previous problem. It worked out to 4. So I'm not going to rewrite all of that stuff. I'm just going to get 4. A really important thing to notice from these first two examples is that function composition is not commutative. What commutative means is that you can switch the order that things are happening in. So for example, addition is a commutative operation. 2 plus 3 is the same thing as 3 plus 2. Switching the order doesn't change the answer. Multiplication is also commutative. Things like subtraction and division are not commutative. So not every operation has that property. Function composition, as we can see, is not commutative. F of g of 1 and g of f of 1, by switching where the f and the g show up, I get different answers. Okay? Let's try one more, g of 0. This one's interesting because we are using the same function twice, which you can do with function composition. Functions can be composed with themselves. So this is equal to what? G of 0. So nice thing about polynomials is if you plug a 0 into a polynomial, you end up with just the constant term. Hopefully you can see why that's the case. If I plug a 0 in for this, all that's going to be left is that constant term. So g of 0 is 5. And now I need to plug that 5 back into g again. That's 5 squared minus 2 times 5 plus 5. 5 squared is 25. This would be 10. So 25 minus 10 is 15 plus 5. That would be 20. Okay? So that's a little bit of work with those function composition concepts. We're going to attack this from different angles. We're still evaluating composite functions at specific values, but this time, instead of having a specific rule for each function like we did up here, we have instead a table of values that f and g take on for a few specific values of x. So let's start here. I want to find f of g of 0. Well, starting from the inside, what is g of 0? I find the g column, and I find what happens when x is equal to 0. I get a 5 for that. So that is the same as f of 5. But what is f of 5? Well, I find 5 in the x column, or x row, and in the f column, I get a 0 for that. So that's equal to 0. You notice, again, the input from this first function the output, from this first function, the innermost function, becomes the output for this second function, the outermost one. Next up, we have g of f of 15. So that's the same thing as g of, what is f of 15? Here's 15, here's f, it's equal to 5. G of 5. What is g of 5? Here's the row that has 5 in it. G of 5 would be 15. So we've got a 15 there. Next up, f of 5. So this is another example where a function is composed with itself. What is f of 5? Well, we found f of 5 over here. We could also look it up in the table really easily, but it came out to 0. So f of 5 is 0, which means I am now finding f of 0 in my table. Here is 0, here's f, that's equal to 15. Okay? Next up, we've got an example where we're composing a function with a function with a function. So this is multiple function composition steps happening here. But it's the same concept, we just work from the inside out. So this is f of g of, what is f of 10? Here's 10, here's f, it's just 10. Now I have to take g of 10. What is g of 10? Finding 10, g also gives me 10 there. Now finally I'm finding f of 10, which again, we already found that here. It was just 10. So 10 showed up a lot, but that's because there's 10s all throughout this row right here. Done. Okay? Fairly straightforward once you kind of get the idea behind how function composition works. We can take another perspective on this. We can use graphs to do these types of problems. So again, I'm just evaluating compositions of functions for specific inputs, 1, 0, -2, 3, for example. But I'm using graphs to find the corresponding outputs for things. So for this guy, I want to find f of g of 1. But what is g of 1? Well, here it says that this pink graph is g. And I find my input of 1. The corresponding output is -1. So this becomes f of -1. What is f of -1? Well, I find -1 on the x-axis for my f graph, which is over here. And I find its output. It gives me a -2. -2. And we repeat this process for these other 4 problems. What is f of 0? Well, here's 0 on my f graph. I plug that in, and I get -3. So this is the same thing as g of -3. But what is g of -3? Well, go find -3 on the x-axis for my g graph, plug it in, I get -1. Pretty simple, right? The next 2 problems are composing one of those functions with themselves, f of -2. So evaluating the f of -2 on the inside, find -2 on your f graph, find its corresponding output. It's -2. -2, it gets mapped to itself, is another way of saying what's happening there. We just did f of -2. It's still -2. Last one, g of 3. What is g of 3? Find 3 on the x-axis for g, plug it in, it gives me an output of -3. Now we're finding g of -3. So now go over here to -3. It corresponds to an output of -1. Okay? Those are very straightforward once you get the idea behind what we're doing here. All right. Having done some practice with composite functions, this example is really the most important one as far as how we're going to use this in the parent class. So now we're not just plugging numbers into functions. Now we are trying to take a given function and think of it as a composition of 2 simpler functions. So how do we do this? Well, if you see how the instructions are indicating us or are telling us what to do, We want to write each of these functions in the form f of g of x by identifying a function f and a function g such that this composition is equal to what we're given. So the key here, and this won't work for every single one of them, but it will work for most of them. Notice that g of x is inside parentheses. We want to look for something that's inside something else. So for this first problem, I have 3x minus 4 in a set of parentheses. That indicates that I should use g of x equals 3x minus 4. That's the thing that's sitting inside this other function. Now, how do I get f of x from that? What you want to do is find whatever part of this function you're calling g of x and remove it and then replace it with just an x. So that would become x to the 7th power. That would be f of x. Now, hopefully you can see that if I compose these functions by doing f of g of x, I would get exactly this function because I'd be plugging g of x in for the x here, which gives me this. Okay, so this would do it. What about for this function? This is an exponential function. I don't see a set of parentheses anywhere, but you can still think of this as a composite function. And the key here is to set the g of x, the thing that we normally think of as the inside function, equal to the entire expression in your exponent, x squared minus 2x to the 5th. That way, f of x is what? Well, remember, we take the thing that we represented as a g of x, swap it out for just x. That would read 5 to the x power. Okay, so as a function, as a composition, f of g of x would take this expression for g of x, plug it in for the x right here, and it would give me this. Next one, I do have a set of parentheses here. So we're going to follow that guideline where we set g of x to whatever it is that's inside a set of parentheses. Square root of x over 7x cubed plus 4x minus 1. That's what I'm seeing in there. What would f of x be? Well, again, find g of x, pull it out, replace it with an x. That would leave me with natural log of just x in there, ln of x. And that's it for that one. What about this one? I don't see a set of parentheses here. We're looking at the 9th root of the log of x. But even though there's no parentheses, that log of x is technically sitting inside of the radical. So the logarithm is like the inside function here. I'm going to set g of x equal to log of x. If we were to remove that log of x from the original function and replace it with just x, we would have the 9th root of x. And that is kind of how we want to think about that, okay? Relatively short one this week, but that's all we have for composite functions.